Hey there, chemists. We're going to keep talking about thermochemistry and heat as it's related to chemical processes. Today, we're going to look at how we calculate the heat for a chemical change. We call this calorimetry. It's how we measure heat indirectly by looking at what a reaction does to something else that we already know about. Here's a picture of what we call a calorimeter. It's just an insulated container with some medium, usually a reaction mixture done in aqueous water, and by looking at how the temperature changes for that surroundings, the water mixture itself, we can indirectly figure out how much heat was absorbed or released by the reaction. Let's dive right into a problem and we'll show you how this works. So here it says we mix a mass of sodium carbonate with a certain number of moles of hydrochloric acid. The mixture changes from 22 to 26 Celsius. And we're going to assume that the reaction mixture has a specific heat that's the same as liquid water. Makes sense because if we're using aqueous hydrochloric acid, it's mostly water that's absorbing that energy. They also tell us the total mass of the reaction mixture that we're going to use. So let's write a balanced reaction, figure out the limiting reactant, and I'll show you how we get what's called the enthalpy change for the reaction, which you'll notice we use the letter delta H again. So the chemical reaction is between sodium carbonate and hydrochloric acid. So let's just rewrite those formulas. Sodium carbonate is Na2CO3, hydrochloric acid is HCl. Now, anytime you mix an acid with a carbonate, you should remember from earlier in the course, you form carbon dioxide. This is how you make CO2 in the laboratory. It becomes CO2 after its initially carbonic acid, H2CO3 is what you would write if you wrote this as a double replacement reaction. But remember that very quickly turns into CO2 and then a water molecule. So another product is water. What else are we missing? Well, there's the spectator ions, which I'm going to include here just to make it a completely balanced reaction, and that's sodium chloride. Speaking of balancing, you need a 2 in front of the HCl and a 2 in front of the NaCl. There's our reaction. Now, to get the heat change for this, we need to do a couple of things. Remember from our first lesson that we said Q system plus Q surroundings is equal to 0, and that's still true. Our system is now our chemical reaction, and the surroundings is what we're actually measuring using a setup like this kind of calorimeter. So for the system, we incorporate this new delta H term, which stands for the enthalpy change of a reaction, and we multiply it by how much of a reaction we have. I'll explain what that means in a moment. The surroundings is just the temperature change of the surrounding mixture, which might include the reaction materials themselves, which in this case it does because it's an aqueous reaction. You set those equal to 0. So the new term here, delta H, refers to the enthalpy change for a reaction, and we'll see it's kilojoules per mole of reaction. Now the N is actually not moles of a substance, but how many moles of this reaction do we have? And to figure that out, we need to determine the limiting reactant. So they give us information about both reactants. If you go back up and look at the question, we have a mass of sodium carbonate and then moles of HCl. Let's turn those both into moles and just compare. Our moles of sodium carbonate is the mass, 2.01 grams, divided by the molar mass of Na2CO3, 106, and I get 0.0190 moles. The moles of HCl is actually given, 0.025. Now remember, you have to compare the ratio for each one. Because the coefficient of HCl is 2 and the coefficient of Na2CO3 is 1, you actually determine that HCl is your limiting reactant. Hold on to that. We need that when we come back to this equation over here. So we're looking for delta H. What's our delta H value? We'll rearrange this and solve for delta H. You get delta H as negative MC delta T divided by N. And this N is moles of the reaction, which is based on your limiting reactant, and you'll see how we use that. So we have the negative symbol. Our M is the total mass of everything. Up above, it says it's 27 grams. It tells us that C is the same as it is for water, 4.18 joule per gram degree Celsius. And the delta T is the final, 26, minus the initial, 22. Now the N, I'm initially going to just write how many moles of limiting reactant we have. Let's take that limiting reactant and just put it right there. But that isn't moles of reaction. We need to use our coefficient ratio to turn this into how many of these reactions actually occur. So there's 2 moles of HCl for every one of these reactions and that's how you write it, 2 to 1. Now, we're almost done. This gives it to us, if you look at your units, moles HCl, moles of HCl, gram, degrees Celsius, degrees Celsius. This is joule per mole of reaction. We want kilojoule, so we need one more conversion to make this work. Just get out of joules and into kilojoules. And once you do the math, you get a value of negative 36 kilojoule per mole of reaction. That's how they write these units. So for every one of these reactions, you release 36 kilojoules. That's what the negative sign means. That means this is an exothermic reaction, which makes sense. The surroundings heated up. The surroundings absorbed that energy because the reaction released that energy. And system plus surroundings is equal to 0. Okay, so that's how we get the delta H of a reaction from indirectly looking at what it does to the temperature change of water in this case. I want you to try the one right below it, hit pause, and see if you can do the same thing. There's a reaction that occurs. They give you information about both reactants. They tell you the initial temperature and the final temperature. It's all mixed in a mass of water. Follow the same kind of process and see if you can figure out what the delta H is for this one. Okay, let's see how you did. So the reaction is barium nitrate and sodium sulfate. So I'll write both of those. Barium nitrate and sodium sulfate is a precipitation reaction. If you remember from last semester, you will form barium sulfate and then sodium nitrate. There'll be 2 sodium nitrates once you balance them. Now there's 1 mole of each, so there's a lot less to calculate for limiting reactant. There's actually no limiting reactant. It's perfectly stoichiometric. So we're going to have 1 mole of reaction in this case because the coefficient of everything is 1. So that's a little simpler than the first one. And then we use the equation we derived last time. Delta H is negative MC delta T over N, which in this case is just 1. And do we know everything we need to? Yeah, we know how much of everything we have, we know the specific heat, we know the delta T, and we know the N. We just have to plug it in. Now the M is bigger than you might have thought. It is 2,000 grams of water, but don't forget there's also a significant amount of each of the reactants, and because it's all mixed together, the reaction components sort of become the surroundings as well. So I need to include the mass of a mole of barium nitrate, which if you add up a barium, 2 nitrogens, and 6 oxygens, you get 261.35 grams. I also need to add the mass of a sodium sulfate, which if you add up Na2SO4, you get 142.04. So that's our M for the entire thing. C is 4.18, and delta T is this 28.1 minus 25, and then our moles of reaction is just 1 because there's 1 mole of each, and the coefficients are 1. Don't forget, you also need to convert into kilojoules, and then once you plug everything in, you get another exothermic reaction at negative 31 kilojoules per mole. So if a system forces the surroundings to heat up, that means it's exothermic, and delta H will be negative. That means if we have a delta H that's positive, the surroundings is going to have a temperature decrease. We'll see that every time, as well as when we go into the laboratory to do this. Okay, so that's how we use calorimetry, meaning measuring heat, measuring calories, to indirectly figure out the magnitude of the change in enthalpy of a chemical reaction by looking at what it does to the change in temperature of some surroundings, usually an aqueous mixture. The other thing I want to talk about today is how do we use reference materials to calculate these delta H's, not from doing an experiment, but looking at tables of what are called bond enthalpies or bond energies. This is based on our structures. So we're going to go back to first semester chemistry a little bit and draw structures for reactions, and we'll see that the delta H value is based on the changes in the bonds. So here's a combustion of propane. Remember, combustion is just oxidation of a hydrocarbon to make CO2 and water. And they first ask us to draw just a molecular representation. What does this look like as a picture? Well, there's a propane molecule, 3 carbons and 8 hydrogens. There are 5 oxygens, so 1, 2, 3, 4, 5. Remember, oxygen is diatomic with a double bond in between each. It forms 3 CO2 molecules. Those are doubly bonded carbon oxygens. And then 4 water molecules with OH single bonds. And we can actually use this to calculate an expected delta H for a reaction with tables of bond energies. It's based on the fact that the change in enthalpy of a reaction is the sum of all the bonds that are broken minus all the bonds that are formed. What you break in the reactants minus what you form in the products. Because every time you break a chemical bond, energy is absorbed. And every time you form a chemical bond, energy is released, hence the negative sign. And we just use a table to look up these numbers. So for this example, we have 8 CH bonds, if you just count how many of these bonds we broke in the starting materials. We also have 2 CC bonds, almost forgot those, in the propane molecule. And then we have 5 oxygen-oxygen double bonds. And we have all those values over here on the right. Now, what did we form? Well, we formed the CO2 molecules, and there's actually 6 of these CO double bonds. So 6 times a CO double bond. And then we formed 4 water molecules. That's actually 8 OH bonds. So we have these values from a reference table right here. We plug in the algebra, we plug in the arithmetic, and we get a delta H value. So a CH bond is worth 414. These are kilojoule per mole. A CC bond is 356 kilojoule per mole. An OO double bond is 494 kilojoule per mole. The CO double is 803. And the OH single is 459. Get a calculator and plug that in. You'll find that it's negative 1996 kilojoules per mole. So for this type of process, we always need to draw a picture or at least visualize it so we can see what bonds break and what bonds form. So try that for these last 3. These are actually a little simpler than the example we just did. Draw these as pictures, figure out what's breaking, what's forming, and then use the table to get a delta H for each one of these, and then come back and see how you did. Okay, let's see how you did. So the first one is the synthesis of HCl from a hydrogen molecule and a chlorine molecule. Those are just single bonds, and you make 2 HCl's. So delta H is we're breaking an HH, that's 440. We're breaking a ClCl, that's 240. And we're forming 2 HCl bonds at 430 apiece. You should have gotten negative 180 kilojoules per mole of reaction is what you'd really say for one of these. Right next to it in B, we're bringing together a hydrogen molecule and an oxygen molecule to make a peroxide. That's what a peroxide looks like. So you're breaking 1 HH bond, you're breaking 1 OO double bond, and you're forming 2 OH bonds. There they are. And don't forget the 1 OO single bond in the middle. So I have to negate both of those because you subtract everything that you form, because every bond that's formed is a release of energy. Every bond that's broken is an absorption of energy. You do the math, you should get negative 191 kilojoule per mole reaction. And the last one, this is hydrogen and oxygen making water. So we have 2 hydrogen molecules, 1 oxygen molecule making 2 water molecules. The delta H, you're breaking 2 HH single bonds, 1 OO double bond, and you're forming 4 OH bonds at 459 apiece. You do the math, you get negative 462 kilojoules per mole of reaction per one of those. Okay, so today we talked about how to get the delta H of a chemical reaction, how much heat is absorbed or released by a chemical change. We can use bond energies. These are reference values based on average bond energies, and calculate what we should get by looking at a structural representation, or we can get it indirectly through what's called calorimetry, looking at how much energy is released or absorbed to some surroundings, and indirectly having that tell us how much heat is related to the chemical reaction. In our next and last lesson in this unit, we will look at how we use other reference types of information to also get the delta H of a reaction. Thanks for watching.